the students that are running the student talks. So all of the students should check your email and make sure that you know what's going on. You know, this is just a service announcement.
Okay, maybe I'll start with the blah blah. Oh, it's 9:05, so let's get started. Welcome everybody to week 3 of TASI. I hope you're all enjoying it and hanging in there and not getting too tired out yet, and learning a lot of good physics. Today's lectures will be first about dark matter experiments, in particular direct detection, but from Eric Dahl, who I'll introduce in a minute. Followed by neutrino mass models from André de Guerre, and then in the afternoon, talk on our lecture on quark and lepton flavor physics from Lisa Everett. A couple of things I want to remind you about. First of all is the discussion sessions. They are on Wednesday and Friday at 3:45 p.m. TASI time. Wednesday, we're going to have Eric Dahl and Lisa Everett. Friday, we're going to have Kev Abazagian and Ben Jones, who will be giving their lectures starting a little later in the week. And Andre, who's also giving lectures this week, will try to hang out in the coffee breaks, which are at 1:30 p.m. TASI time every day, as you probably all well know at this point. Just to remind you also about the Slack channels. You can ask physics questions in the physics chat. And also there's announcements like which room to go to for the discussion sessions and stuff like that in the general channel. And for the lectures, as we've been doing, please put your questions in the chat and Eric will answer them as he goes along in his lecture today. So this brings me to, it gives me great pleasure to introduce this morning's first lecturer, Eric Dahl from Northwestern University. And he's going to tell us about dark matter experiments, in particular direct detection. Please go ahead.
All right, thanks. Can you confirm that you hear me still?
Sure.
Yes,
No
okay,
problem.
good. Thank you. Just wanted to check. Okay, so I'm going to be doing this lecture from a Google Jamboard. So if people want to click on that, you can get view access. That's posted on the Twiki. And yeah, this is dark matter direct detection for theorists. So I am not a theorist, so this is going to be an interesting talk because I don't know how many direct detection experimentalists you know, but as far as experimentalists go, we tend to be very far on the instrument building side. We like to grab wrenches and make leak-tight vacuum systems and things along those lines. And sometimes it seems like most of our cross-section with theoreticians is through plots like these. You know, we do all of our work and then typically we don't find dark matter. And so we draw one of these curves and we exclude some parameter space. And then theoreticians take that and say, okay, we can cross off these models. And that's not really a healthy state for the field, right? So I think the goal of the next couple of days for me is to, communicate what goes in to making these limits. I mean, is it really true that CDM is slight and CREST 2 over here? Hold on, give me just a moment because every time I switch to this, my pointer stops working for a moment and let's see, can I get the, there we go. Okay, so, is it really true that those two limits are comparable to each other? What's going on with the neutrino floor? Is it worth having 3 different identical experiments looking for spin-independent WIMPs? What's the difference between spin-dependent coupling and spin-independent coupling? And, here we've got, a bubble chamber and xenon on top of each other. Is that worthwhile? Is one better than the other? And why do we have all of these different experiments in the first place, right? So these kind of questions that I think it's important for people to understand how to interpret the things that are going on behind these plots that don't come across in a single line. And you might be surprised by some of the shortcuts we take when we do these. Other interesting thing about these lectures are that I didn't teach this last quarter. So this is my first experience giving a lecture remotely. So please bear with me. Today's lecture is going to be kind of, I guess, what passes for a Blackboard style lecture now. It'll be on Google Jamboard. Tomorrow is going to be more of a seminar with slides. One thing I've learned about Google Jamboard, or just trying to use the stylus in general, is that it takes me a while to get warmed up. So give me a moment just to draw a doodle and actually tell a little bit of a story. So we're doing dark matter detection for theorists today. The other day I did dark matter detection for a 7-year-old. And something kind of interesting came out of it, actually. My handwriting will get better as we go here. So this is me talking to my son, who's sitting on the floor, and he's 7. And I was asking him, okay, so I'm going to give these talks about dark matter detection. What would you want to know? He said, Dad, I want to know what dark matter is. I said, well, okay, that's great. I want to know what dark matter is too, but that's not what I'm going to be talking about because we don't know yet. And he said, well, I know you build detectors. How do you build detectors for something when you don't know what it is? Which of course is a good question. And then he also said, well, what sort of detector do you build anyway? I mean, is it like a smoke detector, which is one sort of detector he knows about, or is it like a fire detector? And sorry, is it more like a metal detector? It's like, you mean like we walk through at the airport? It's like, no, like, those guys at the beach that are going around and, I don't know, looking for buried treasure or something. And, this was kind of a fun conversation for me and my kid. It's also fun to draw. But I like this picture of trying to look for dark matter as buried treasure. The other interesting thing here is that, in a way, this kind of does capture 2 completely different types of direct detection, right? A smoke detector, if you don't know, that is an ionization drift chamber, not that different from the particle style dark matter detectors, which are what I'm going to be talking about today. Whereas a metal detector, okay, there's some inductive pickup coil there. That's not that dissimilar from the way you look for bosonic wave dark matter. So I kind of thought it was interesting that a first grader picked up on just the 2 fundamental different ways that we look for dark matter. Okay, so I'm going to consider myself warmed up now. A little bit of overview of what's going to happen these next 3 days for dark matter detection. Today, we're going to go over the ideas behind the detection of particle dark matter. So what are our signals? What are the basic assumptions that go into how we build these detectors? A little bit on how to speak experimentalist so that you understand the assumptions that we're making, and things like, what do we mean when we say we have a 0 background result? Kind of like if you speak theorist, we have to understand what you mean when you say you have a very well-motivated model. You need to understand what we mean when we say we understand our backgrounds with the appropriate grains of salt. Tomorrow, it's going to be less of lecture style, more of seminar style, looking at real examples of these dark matter detectors, and specifically, how is the real world different from this idea that I'm painting today? Kind of, what goes wrong? Because until you understand what goes wrong, it's hard to understand when you might want to be skeptical of a result. And that's, one thing that we should come out of this with is a healthy skepticism, because that's what keeps the field honest. Then Wednesday's going to be interesting. This is not planned, but Wednesday morning, immediately before this lecture, there is a new result coming out from Xenon 1 ton. The rumor is that it's not going to be just a limit. It's not going to be a discovery, but it's going to be one of these places where they see something that they can't explain away as a background, and they will, I'm sure, offer an interpretation of, if this is new physics, what new physics might it be? Not that they're saying it's new physics. So that'll be interesting to watch. Encourage everybody to tune in here to the live stream. There's also a Zoom for this. We're not allowed to post the Zoom publicly because we don't want Zoom bombing, but if you want to be able to ask questions during this, then we can share the Zoom link over Slack. So I'm going to watch that before giving the lecture on Wednesday. After that, we will certainly talk about it during Wednesday's discussion session. We may talk about it a bit, give a summary of it during the lecture on Wednesday. Also Wednesdays when I want to spend some time talking about how to detect wave dark matter. Everything today and tomorrow is going to be about particle dark matter. But there's some really interesting things about detecting wave dark matter. It's a completely different world, one that I know a little bit less about, but there's some neat tricks there. So, okay, today you're stuck with my handwriting. Hopefully this is legible. Tomorrow it'll be a little bit more slides. Okay, so let's get going. So today it's what are the basic ideas behind direct detection of dark matter. And for particles, almost every detector that we look at, we're really just looking at elastic scattering of WIMPs from our galactic halo in our detector. So dark matter particle, I'm going to write them all as chi. It doesn't have to be a neutrino. This is going to be completely generic as to what the dark matter is. It's just got to be something with some mass that comes in and elastically scatters off something in our detector. So same particle coming in is going out. That's what I mean here by elastic scattering. What's going on in the detector may or may not be elastic. And if we want to say very generically, what's this signal going to look like? Well, we can just start doing kinematics. This is all non-relativistic elastic scattering, just like balls on a billiard table. Non-relativistic dark matter in our galaxy is going at about 1,000th the speed of light. And so we can look at and say, oh, well, how much energy do we get? And there are two regimes that we should look at, right? So we can first say, what if the dark matter is light compared to whatever it is in our detector that it's bouncing off, and just call that MD for the detector. So this is the picture where, and sorry if this is a little bit simplistic, but if you have a ping pong ball bouncing off a bowling ball, how much energy do you get off of that? And when you say it that way, it's like, well, your momentum transfer, the maximum momentum transfer that you can get is just twice the momentum of the ping pong ball coming in, right? So our maximum momentum transfer is 2 beta m chi, and so the maximum energy that we might be able to get in our detector here, 2 beta squared m chi squared over md. So if it's light dark matter, the lighter the dark matter is, the less energy that we can get coming out. Okay, but if we're on the other regime, so now maybe instead of a ping pong ball bouncing off of a bowling ball, now we've got a bowling ball running into the ping pong ball. We're going to say the dark matter is the bowling ball, it's coming at us, and we've got a very light detector. So for instance, this could be a classical WIMP bouncing off of an electron. What happens in that case? Well, again, the maximum momentum transfer is just, well, it's the same relative velocity, so it's still twice that relative velocity times the thing that's light. Just the thing that's light now is whatever in our detector is bouncing off. And so the maximum energy you get out is just that kinetic energy. In other words, if the dark matter is going at 10 to the minus 3, then whatever is recoiling in your detector might come out at 2 10 to the minus 3 as its max velocity. So you have these two regimes, and we can connect them. So if we just want to say how much energy can you get in a direct detection experiment as a function of the dark matter particle mass. Okay, well that's, the shape here is that, okay, if the dark matter is light, then you get more energy for heavier dark matter, and then it plateaus somewhere. So if our detector is made of protons, for example, the most energy we're ever going to get out of this is beta squared times the mass. So protons are GeV, we can get a keV in our detector. keV, so that's like an X-ray photon. We can detect X-ray photons, so that's an amount of energy that you can at least imagine detecting. And if the dark matter is kind of GeV or heavier, proton mass are heavier, then that's what you're going to get. But you won't get more than that. If you want to get more energy than that, then you can go to a heavier target. So maybe instead of bouncing off of a proton, we're bouncing off a xenon nucleus. Rough numbers, this is now 100 GeV. Xenon's mass number is about 130. And so you can get 100 keV out of this. And now that's a relatively strong signal to detect. But of course, if the dark matter is light, then you don't do well in xenon because you don't have a good kinematic match. So if you're down at a GeV or below, xenon doesn't work. If you want to go even lower in mass, then maybe you start talking about bouncing off of electrons instead. So if we draw electrons on this plot, you're talking about now just EV energy depositions for dark matter down to kind of MeV-ish mass. And that's basically the range of what people do in direct detection right now. We've got some experiments that look at electron scattering, some that look at scattering of light nuclei, some that look at scattering of heavy nuclei. And they're each looking at, WIMPs or asymmetric dark matter or dark sector new physics. And there is one thing I want to call out here. If we're looking at bouncing off of nuclei, this is really the whole story, as long as you're talking about elastic scattering. If you're talking about scattering off of electrons, we can't think of this as being elastic on the detector side anymore, right? Because EV energies, this is chemistry. This is, you're taking the electron barely from bound state to state. So you can't just think of this as scattering off of free electrons the way for nuclei. You can think of it as scattering just off of free nuclei and ignore the other things going on. For electrons, chemistry matters, band gaps matter. Because you're really having dark matter interact with the bound state of the electron, which means you've got the thing that the electron is bound to as part of it. So you can get more than just an EV from scattering off an electron, but it depends on what material you're in. So electron scattering experiments are a little bit more complicated. We'll talk about them a bit on in tomorrow's lectures. Today, we're still going to focus mostly on dark matter bouncing off nuclei. Okay, so that's the basic story from a kinematic point of view.
Eric?
Yeah?
There's a question in the chat that relates to that
Sure.
plot.
Okay, is the x-intercept interpreted as threshold energy to produce a signal? And is that set by kinematic properties of the detector? Yeah, so the x-axis here is the mass of the dark matter particle. It's really the y-axis is, the y-axis here is what threshold energy do you need? So to have an effective xenon-based detector, so if your detector is looking for xenon nuclei being struck by dark matter, if you're looking for dark matter at 100 GeV or above, you'd better be able to see at least 100 keV recoil, because that's the maximum energy that this is going to get. If you're building your detector out of protons, you have to be able to see at least a keV proton recoil, because that's the maximum energy it's going to get. So this is telling you what threshold do you have to reach to be remotely useful as a dark matter detector. And that's going to be a function of both what is your detector made out of and what mass dark matter are you looking for. In general, you want your detector to be made up of things that are the same mass as the dark matter, if you can do that. So we'll talk about this in a little bit more detail here with some actual numbers. Taking as an example the case where where we're building our detector out of argon nuclei. Why argon? Because we know we can build enormous detectors out of liquid argon, and we haven't talked about it yet, but these are rare event searches, and so you want an enormous detector. So let's suppose we're building our detector out of argon, meaning we're looking for dark matter scattering off of an argon nucleus. We've talked about the kinematics, and at least we've talked about the kinematics if you've got dark matter of one velocity coming in and what's the maximum energy you get. Now we want to turn that into kind of a whole recoil energy spectrum. And it's not just the kinematics that goes into that. We've got, some particle physics telling us, what's the differential scattering cross section here. We've also got some astrophysics coming in. So what is the actual velocity distribution of the dark matter particles? They're not all going at beta of 10 to the minus 3. It's got some spread to it. And we'll talk about each of those in the next slides. But if we know the astrophysics and we've got some particle model for how the dark matter interacts, then that gives us some spectrum in our detector. And our detector is going to have some threshold. So typical threshold for an argon detector is somewhere between 30 and 40 keV for detecting argon recoils. So we'll call that ET, our threshold. And now we take that and we look for the signal. We take some data, and assuming that we don't see an excess over background, then this turns into one of these limits that looks like a Nike swoosh. So we get something that goes like this, where we've excluded everything up here. The x-axis here is what dark matter are we looking for. The y-axis here is something about the interaction strength, usually a cross-section. So how do we get from one to the other here? Well, we can read off a couple of things right here. In this experiment, our threshold was at about 30 keV, and you can see that, okay, for a heavy dark matter particle, a WIMP close to a TeV, we were seeing most of the scatters. Sorry, I skipped this. This rate over threshold here, what we're really plotting here is what fraction of the dark matter scatters are over the energy on the x-axis. So here, if we're looking at a 500 GeV, we're seeing, more than half of the events that a 500 GeV dark matter particle would make in the detector. Down at 50 GeV, this is really starting to fall off. And so the way to think about this is this threshold is really what's setting the low mass reach of this curve. And in this case, it's falling off roundish 50 GeV. So this is going to be around this left edge of the limit is going to be around 50 GeV on the plot, on the limit plot. And if we wanted to see lower mass dark matter without changing our target, we'd have to lower the threshold, and then this would lower accordingly, just based on the kinematics. If we look at this side of the limit curve, every limit curve that you see in any of these plots, you always have this piece here that has a slope of 1. And the reason for that is just that as the dark matter gets heavier, there's less of it, because we know what the mass density of dark matter is. So heavier dark matter particles, it's, the number of dark matter particles you have to try and find just goes like 1 over the mass. And so as mass goes up, your sensitivity goes down just because your flux goes down. So that's, I don't know, that's the basics of the swoosh. Let's dig in now a little bit more to what's going on with the particle physics models here. So what we have to do on the experimental side is we have to basically choose some low energy effective field theory here. And in fact, the field almost always chooses one of 2 low energy effective field theories, whether you're looking at scattering off of nuclei or electrons. And there are a couple of pieces of physics that come into this. One is that we always end up saying that the cross-section is going to go like the reduced mass of your scattering system squared, and it's going to be independent of velocity. So looking like reduced mass squared, this is almost looking like the Fermi 4-point interaction, right? And that's kind of where this came. The reduced mass squared comes from the same place. Being independent of velocity is a little bit more of a choice, because there certainly are, there exist effective field theory operators that go like, the relative velocity between the particles squared. But we're at velocities down of 10 to the minus 3, and so these are all very highly suppressed. And so unless you really tune your ultraviolet theory such that the operators that are independent of velocity are suppressed for other reasons, they're always going to dominate. And so any limit that I've seen people draw, unless you're really going after a specific EFT operator, all the normal limits assume that the cross-section is velocity independent. And for similar reasons, those operators give us isotropic scattering. And so, knowing that it's an isotropic scatter independent of velocity, that's enough now to figure out the shape of the differential scattering spectrum. The other piece of, oh, sorry, I just glanced at the chat here. Okay, sorry, good questions. Coming back here, this shaded region is the region that is excluded by the experiment. So any experiment is going to exclude some region of interaction strength for some WIMP mass range. So in this case, for WIMPs heavier than 50 GeV, if they had a sufficiently high cross-section, you would have excluded it. How low you go in this direction basically depends on how big was your detector. The bigger the detector is and the lower your backgrounds, the more rare interactions you can look for. You can basically, from an experimental point of view, think of this as just a multiplier affecting your rate. So if you can put a limit on how many events you saw, that turns into a limit on the interaction strength. What does E sub r stand for? That's how much energy you get in your detector. Sorry, I didn't define that either. That is the energy of your recoil. So we don't see the dark matter particle, we see the thing the dark matter particle hit. And so generically we call that a recoil. In this case, it's a recoiling argon nucleus. So we're looking at a recoil energy of a few keV for a dark matter particle that has a 50 GeV mass coming in and bouncing off the argon nucleus. Okay. I'll try to remember to glance at the chat in between slides. Okay, so coming back here, so we talked about some of the particle physics that goes into getting this differential recoil energy spectrum. And if you're looking at scattering off of protons or off of electrons, that's everything that you need to know. And then you're just going to make a limit on your scattering cross-section for dark matter bouncing off protons or electrons. Okay, so y-axis rate over threshold. Yeah, I forgot to say that, and then I put it in halfway through, but it was a little bit jumbled. So rate over threshold means, okay, so if we go back a slide, rate over threshold means what fraction of your events are giving you a recoil energy over the value on the x-axis. So this is an energy spectrum, but it's a cumulative distribution instead of a differential energy spectrum. It's easier for experiments to think of it this way because we have a threshold and we only see events that are above our energy threshold. So again, this is the energy that we get in our detector. And so if we have a threshold in our detector then we get to see some fraction of the events. And so this was the point here. For a 500 GeV WIMP, we would see most of the events in this particular detector. But if we wanted to see a 5 GeV WIMP, we'd have to get our threshold much lower. How do we lower ET in practice? That we will talk about tomorrow. We'll talk about a little bit today, generically, what are the signals that we turn into an energy measurement. But how you lower it in practice, yeah, these are low energies that we're talking about. Measuring a KeV, again, that's like seeing one X-ray photon, which you can do, but we're trying to do this in enormous detectors. We'll come back to that. We'll come back to that question. Okay, coming back here, maybe I should pause and see if there are more similar questions on this slide, since a few of them have been coming up. Okay. So one thing that we want to do when we say we assume isotropic scattering, is that taking into account the dark matter wind? Okay, so when we say isotropic scattering, what we mean is that for a given incoming dark matter particle, that it's an S-wave scatter. So if I tell you the velocity of the dark matter particle coming in, it can bounce off our target equally in all directions, which basically means that the recoil energy we get is a flat distribution from 0 recoil energy, forward scattering, up to the maximum recoil energy that we calculated back here. So isotropic scattering just means that the actual energy that we see is a flat distribution from 0 up to this Emax for a given dark matter particle coming into our detector. The dark matter velocity distribution itself isn't isotropic. We'll talk about that in the next slide. Okay, so we haven't got to this point yet. One thing we want to be able to do in direct detection experiments is compare results from different detectors, right? So suppose we've got a detector made out of argon and a detector made out of xenon, and here we've normalized things such that you could compare the rates between these based on the assumption that you have the same mass. So compare 1 ton of xenon to 1 ton of argon, for example. And you have to make some additional assumptions when you want to compare those two detectors. It's one thing to say, if we wanted to, we could just say, we put a limit on the dark matter argon nucleus scattering cross-section, or we put a limit on the dark matter xenon scattering cross-section. But we don't want to do that. We want to take those and turn them into limits on the dark matter proton scattering cross-section. And when we do that, we have to make an assumption about how do you get from the cross-section on one nucleon to the cross-section on a whole nucleus. And this now brings in some more model dependence. So, and there are kind of two basic models that we can look at here. The thing to keep in mind here is that when we're looking at these low energies, so the highest momentum transfer that we would ever look at in these experiments is coming onto xenon, because that's our heaviest target, and we really only get up to momentum transfers of a couple hundred MeV. If you just look at this recoil energy on xenon, that turns into about a couple hundred MeV of momentum transfer, and that gives you a de Broglie wavelength of about 1 Fermi. 1 Fermi is about the size of a nucleus. So for most experiments that aren't using xenon or that are looking at lower energies, this scatter is completely coherent across your nucleus. So you're scattering off of the nucleus as if it's a single particle. But that coherence, that means you have to add scattering amplitudes instead of adding cross sections. The scattering amplitudes can interfere constructively or destructively, right? So when we say we look for spin-independent scattering, what we're really saying is we're looking at models where the scattering amplitude does not depend, say, on the spin of the nucleus, meaning that every nucleon, the spin of the nucleon, so every nucleon contributes to the scattering amplitude with the same sign. And so your scattering amplitudes add and your overall cross-section goes like a squared, except for xenon, you have to worry about the form factor of the nucleus, because for xenon, you are getting to the point where you are starting to lose coherence across the whole nucleus. And in fact, that's why for scattering off of xenon, this falls off a little bit quicker than it does for argon, because not only are you reaching the maximum energy that the dark matter can give to the xenon nucleus, you're also losing this A squared, this A squared enhancement. But typically, when you come down from a UV model, you will get some spin-independent interaction. You'll also get some spin-dependent interaction. Now, this is still coherent across the nucleus, but now nucleons with opposite spin contribute to your scattering amplitude with opposite signs, and so they cancel. Especially for, say, you're scattering off of argon, where you've got an even number of neutrons, an even number of protons. They're all paired up. So you get almost no spin-dependent cross-section for scattering off of argon. For other things like xenon, you do, but actually figuring out what that cross-section looks like for a given nucleus is not easy. And a lot of nuclear physics modeling enters here when you're trying to figure out how do you relate the spin-dependent cross-section on a nucleus to the spin-dependent cross-section on a proton or a neutron. Okay, so we should be aware of that, but this is really a summary of all the particle physics that goes into making this spectrum. The other physics that comes into this, okay, how do we tell whether a recoil is from spin independent or spin dependent? We can't. All we get to see is the recoil energy. If we want to know, are we seeing a spin independent or a spin dependent signal? We have to build a new detector and see if the signal goes away. So for instance, if we saw the signal on argon, we'd know it's spin independent. If we see it on xenon, a typical model on xenon, okay, we can probe much smaller cross sections on spin independent thanks to this A squared enhancement. But typically, you expect much larger cross sections for spin dependent. And so for xenon, it's really kind of a coin toss. If you see something, you don't know whether it was spin independent or spin dependent. So you have to run another experiment. So you run argon, and if the signal goes away, that might be an indication that you're seeing a spin-dependent scatter. Or you isotopically separate your xenon. That'd be a more expensive way to do it. Speaking of expense, is the cost difference between argon and xenon an important factor when building a detector? If you talk to the argon builders, yes. If you talk to the xenon builders, it's not that big a deal. I would say it's actually not the driver. Even for a xenon detector, let's take LZ. LZ comes out to be, well, okay, depends how you count money. Let's call it an $80 million experiment, of which $20 million is the xenon. So it's not, it is a big cost, but it's not the only cost. Whereas for argon, yeah, argon is almost free, except that all the argon experiments now need low background argon. Argon is radioactive, and you need to isotopically separate it or find a source of argon that's low in argon-39 in order to do your next generation of argon experiments. And so suddenly that drives the cost of the argon way up. So to me, cost between argon and xenon isn't important anymore. Okay, these are fun questions. But let's keep going forward here and bring in astrophysics. So this is where astrophysicists get rather annoyed with direct detection experimentalists, because what we do, we say, okay, we've got some velocity distribution for dark matter in our galaxy, and we're just going to assume it's a Maxwell-Boltzmann distribution that cuts off at the escape velocity. So that's our escape cutoff here. And this here, I'm drawing the distribution of the dark matter velocity. And then we add in the fact that we're moving through the galaxy at about the same speed that the dark matter itself is typically going. So this whole distribution shifts, to higher energy because we see a net headwind of the dark matter. So that's a very simple, well-defined model, but it's also very naive, right? There are lots of things you could ask about that this ignores. So for instance, if we're in an involume stream of dark matter, that would completely change velocity distribution. Or if we're in a dark disk that is co-rotating with the light matter, then when we went to the lab frame, everything would be moving much more slowly. So in some respects, astrophysicists will tell us this is a really naive model and it's not right. And we know that, but it's well defined and we don't really know what the right model is because the right model becomes more model dependent. So this is what we choose. And the question that you should ask is this good enough? Does our uncertainty on the astrophysics actually matter? So let's look at that for just a moment. So let's go back to our argon detector and let's imagine we've got two different argon detectors. We've got one that is pretty high threshold, so we were building it cheap on the instrumentation. But let's say we've made this one really big. So it's 500 kilotons. So I don't know. No, sorry, not 500 kilotons. That'd be huge. 500 tons, half a kiloton. So I don't know. Maybe that's like turning a piece of dune into a dark matter detector somehow. Versus, let's consider a detector where we've really worked hard on collecting signal. So we've got a 10 keV threshold, but it's only 1 ton. Oh, no, we'll be a little generous. We'll make it 10 tons. And if we want to plot, what are the relative limits for these going to look like? Well, okay, so they're both Nike swishes because that's what they all look like. If we compare the small low threshold detector to the big high threshold detector, out at high mass, we get about 10 times the sensitivity from the lower threshold and the higher threshold, but we've got 50 times the mass here. So we actually win with the big detector here. So we're going to be, up here a factor of a few for the smaller detector. But the smaller detector, since it's got a lower threshold, can go much lower in dark matter mass. Okay, so if you were looking for, big heavy WIMPs, you might say that the big detector is the better way to go here. But then let's think about astrophysical uncertainties, because none of these limit plots ever include astrophysical uncertainties. And you can say, which part of the velocity distribution are we sensitive to if we're looking at 500 GeV WIMPs? So, okay, if we're looking down at 10 keV, we're seeing most of them. So we're actually exploring a big part of this velocity distribution with our 10 keV detector. Whereas for the 100 keV threshold detector, we're really only seeing WIMPs out in the tail here. So the absolute fastest WIMPs in the lab frame. Which means that now, if a astrophysicist comes on and tells us, oh, you need to include uncertainties, or we've got a better model, change your velocity spectrum here. Well, what happens to our low threshold detector? Well, certainly down at low masses, this limit's going to move a lot, because when you're looking at low mass dark matter, where this curve is turning up, that always means that it's turning up because now you're really only sensitive to these WIMPs at the end. But out at heavy masses, this curve is not so sensitive to that because we're seeing most of the WIMPs regardless of how fast they're going. On the other hand, if you look at the big detector, okay, you're still going to have this uncertainty down at threshold, but because even for heavy WIMPs, you're only seeing the very fastest ones, you also get a big uncertainty here. And you don't see these uncertainties in any of the in any of the limit plots, right? We just don't show astrophysical uncertainties as direct detection experimentalists. We say, we take this Maxwell-Boltzmann model, and here's the limit that you get. So it's something that, as theoreticians, you need to keep in mind that there are systematic uncertainties there. They're not experimental systematic uncertainties, but they're assumptions to the model that go in. And if you don't like those assumptions, then you need to respond appropriately. So for instance, in the past, when we had a couple different experiments that thought they saw a signal, but they're showing up in different places, you can make them all see the signal for the same dark matter particle by changing the velocity distribution of the dark matter particle. Okay, didn't understand why the larger detector probes high velocity dark matter. It's because the larger detector, we said the larger detector had a higher energy threshold. So if we look at 500 GeV WIMPs, so if we go back a few slides, if the dark matter is much heavier than your target, which is the case here, argon nucleus is about 40 GeV. We're looking at, TeV-ish dark matter. No matter how heavy the dark matter is at this point, this spectrum does not change. So any dark matter that's coming in, if we're looking at just 100 keV recoil off of argon, we're only seeing 10% of the interactions. We're only seeing the dark matter that happened to be coming in fast enough to give us this much energy, and then basically we're seeing even those very fast particles when they backscatter. So just looking at this, saying that we only see a small fraction of the dark matter says that we're only seeing the high velocity tail of the distribution, because none of this stuff can give us enough energy to get above threshold. And if you believe that this tail exists, you can still get a good limit out of that. But this tail is where you've got bigger astrophysics uncertainties. And so there are hidden uncertainties in where we drew this limit coming from the astrophysics. That's the punchline. Okay, we're going to change modes now to talk. Larger velocity corresponds to larger kinetic energy, right? Yes. Yeah, more energy to be able to give the recoiling particle. Yeah. Okay, let's shift modes now and talk about the detectors themselves. So let's draw our detector again, and we've got this dark matter particle coming in, and yes, if we, sorry, back to the chat. Yes, if we took into account astro uncertainty, then this detector with 100 keV uncertainty suddenly looks like a less good idea, because it's more susceptible to us having the wrong astrophysics. Now, on the other hand, it could go the other direction. It could be that if the astrophysicists come in and say, actually, we're in the middle of a lot of dark matter that's falling into our galaxy and we're flying straight into it. So we've got a big high velocity tail to our lab frame dark matter distribution. Then suddenly having a high threshold is not that big a deal. The point here is just that we've got two things that with one, that where the relative strength between these two detectors has a big uncertainty. So you would not want to, given that uncertainty, if I were a funding agency, I would rather build a low threshold, smaller detector than a higher threshold, big detector. You want to get low enough in threshold that you're not that sensitive to what's still uncertain on the astrophysics side. Okay, so let's talk about how these detectors actually work. So we've said we've got this particle, this dark matter particle coming in, and it bounces off of something. And we get a track from our recoiling particle. So we only see the thing that the dark matter hit. We measured that recoil energy. And if we zoom in on this, okay, so we've got, this is just a zoom in of that same thing. We've got this thing that gets hit by the dark matter, and then it bounces around in the detector until it loses all of its energy. And bouncing around, meaning, you know, if it's a nuclear recoil, it's bouncing into other nuclei, and you get other nuclei coming off. If it's an electron recoil, it's going around and it's ionizing other atoms around it. And you get this whole damage cascade of all the energy from the initial recoil is now getting dispersed in your detector in some complicated track. And the length scale for this track, if you're talking, you know, any solid state detector, for any dark matter interaction we're looking at, it's going to be of order 10 nanometers. So it is a track, but it's not a track that we can see because we're looking for that track, that 10 nanometer track in a detector. You know, typical dark matter detectors now of a couple of tons, the size of the detector is about a meter. So we've got a 10 to the 8 order of magnitude mismatch there. We cannot resolve 10 nanometers in a 1 meter detector. That's just not in the cards. There are directional detection experiments that are trying to move in this direction, and we're not close to being there yet. What does that mean? That means that anything that we see in a dark matter detector at the energies that we care about, these are all point-like energy depositions. And that's just a consequence of we've got so little energy to work. Even if we're talking about the most energetic dark matter particles, you know, 100 keV nuclear recoil only goes a few tenths of nanometers. And since these things are point-like, we don't get a lot of information for each event. We can basically measure, well, it's list. What can we measure? We can measure the energy of the event. And we can measure that usually in a lot of different ways, or depending on what sort of detector you build, you might measure it as ionization. So somewhere in this track, you've got, you know, impact ionization of a lot of different parts of your detector. You might measure it as heat. So if you're bouncing into other nuclei and they bounce around, that just ends up as heat in your detector. So if you've got a calorimeter, that's what that comes out as. Similar to heat, you could look for phonons in your detector. You can argue about whether heat and phonons mean the same thing. Or you can look at scintillation light being generated in your detector. And if you've got a good dark matter detector, you're probably measuring multiple of these, because measuring multiple of those is what gives you recoil particle identification. So maybe if you've got a recoiling nucleus versus a recoiling electron, you get more in one channel of these versus another. Okay. Other things that we measure, we want to be able to measure where in the detector this happens. Even though we can't see the track, we can still see that point and where in the detector it happened, and we can measure it happened. And that's all the information we get. And that's the information that we have to use in order to eliminate all the backgrounds to this signal. So let's spend some time talking about backgrounds, because that's really, if you're a direct detection experimentalist, you spend basically all your time thinking about what are your backgrounds and how do you get rid of them. So here are tools who can measure the energy of the event. If we can measure it multiple ways, we can get recoil particle ID. We can measure position and time. Which of those are important for which backgrounds? So if we've got an alpha decay going off in the detector, so alpha decay, you know, this is like a radon atom got into our detector, one radon atom, it went off, and you've got this alpha particle flying out. But alpha particles, nature's been kind, all alpha decays are at least a few MeV, typically around 5 MeV. So we can say that as long as we've got any energy information, we can discriminate against alpha decays. Things get a little bit more complicated if the alpha decay is happening, at the edge of the detector, because now we don't get the alpha particle, which is what's carrying away all this energy. We just get the other half of the recoil. So the nucleus from an alpha decay, the leftover nucleus, is about 100 keV of energy. So right where we're looking at matter. But if we're not seeing the alpha particle, it means it was at the edge of our detector. So we can eliminate that based on knowing where the detector happened. For many reasons, we want to toss out any events happening at the edge of the detector. Okay, what else can happen? Well, we can have a neutron. So this blue dot is a neutron, and it can fly through the detector, and it will do something like this, bouncing off of nuclei in the detector. I'm having too much fun doing this. This nuclei bounces this direction. Okay. So this is, if we're looking for nuclear recoils from dark matter, this looks exactly like the dark matter signal. In terms of energy, each of these recoils typically will be about the same energy as our dark matter signal. The only way that we can tag these is because there are multiple of them. Typical mean free path for a neutron. Neutron's a neutral particle, so it just flies through your detector doing nothing most of the time. But then every 10 centimeters or so, it will create a nuclear recoil. So we've got a sequence of point-like interactions that are coincident in the detector. So if we've got position and time, we can see these coincident hits and say, well, dark matter wouldn't do that. Dark matter has a mean free path of, 10 to the 14 centimeters or more. Similar story if you've got a gamma ray coming in. Let's make this one green, orange. So the gamma ray can come in and it can Compton scatter a couple times in the detector. Each time it Compton scatters, that can fly off in the detector. But again, if you can identify coincident events at different locations in your detector, then you can tag this. That's also got about a 10 centimeter mean free path. So knowing position and time in your detector is actually really important. How do we get a free neutron, and how can neutrons penetrate walls of the detector? Well, free neutrons come from, for instance, uranium. Our detectors are close to the Earth. Dirt is about a part per billion uranium. U-238 fission makes neutrons. Those neutrons will fly around. They can penetrate through anything because it's a neutral particle. We put a shield around our detector, but some neutrons make it through that shield, or some neutrons may be generated by trace uranium in our detector. That's one example of where neutrons come from. We'll talk about the actual background spectrum in a couple of slides. But neutrons and gamma rays, you can just think as neutral particles, they have a mean free path. They have a significant mean free path. They can not tunnel through, they can penetrate through material and get into the middle of our detector. But if you've got a big detector, their mean free path is short enough that you can see them interact multiple times. And that's actually for detectors like LZ or Xenon 1 ton, that's the most important way that we tag these backgrounds. But that doesn't work for all backgrounds. So for instance, if we've got just a beta decay happening in the middle of our detector. So say some radon got into the detector and then the radon decayed, and later on you've got some other particle decaying. So radon, you don't need to know this, but radon turns into like lead-214, and lead-214 has a beta decay, and that beta decay is just an electron going off in the detector. There are other beta decays we worry about as well, but they're all, any beta decay spectrum, because the energy is shared by an electron and a neutrino in beta decay, it can have any energy coming out from 0, up to hundreds of keV. So it's, again, right in our energy range of interest. down to 0 energy. So we can't use position or time against this because it's a single point-like event happening in the middle of our detector. If we're looking for nuclear recoils, then we can identify these as electron recoils instead. So that's where particle ID comes in. If we're looking for electron recoils, we can't do that. But remember, if we were looking for electron recoils, we were also looking down at EV scale interactions. And so there it's really, you get saved by phase space. Most beta decays are of order keV. Yeah, their energy spectrum goes down to 0 energy, so you will have some beta background, but you're only looking at a tiny portion of the beta spectrum at that point. So if you're looking at an electron recoil detector, you're saved here by energy. If you're looking at a nuclear recoil detector, you're relying on recoil particle ID. Similar story for neutrinos. So neutrinos can come in and bounce off an electron in your detector. And that's a single site interaction. Again, you've got to use recoil particle ID to tag that. And then we've got one more background that is worth mentioning, which is if you've got a neutrino comes in and bounces off a nucleus in your detector. So this is, I think you've heard by now about coherent elastic neutrino nucleus scattering. And that is for a nuclear recoil dark matter detector that is fundamentally indistinguishable from the dark matter signal. So there's some thinking that coherent scattering of external neutrinos is the end of direct detection, at least for nuclear recoils. Would the neutrinos from beta decay cause subsequent backgrounds? No. Our detectors are not nearly big enough for a neutrino from a beta decay to, for instance, be coincident with the beta decay in our detector. We do get beta decays that will be coincident with gammas. So a lot of beta decays, you'll get the beta decay and a gamma at the same time, and that's good news for us, because then we can use the multiple scattering again if the gamma interacts on its way out of the detector. But there are also what we call naked betas. So a beta decay where the decay puts the resulting nucleus in its ground state. So all you get, I'm going to go ahead and write, what is a beta decay up here? So for instance, you get lead 214 goes to, I guess it's going to go to polonium 214. Do I have this right? Yeah. Or is it? No, it's bismuth. Bismuth 214 plus an electron plus the anti-electron neutrino. That's one of our main beta decay backgrounds. And this bismuth is in its ground state. You don't get any gammas associated with it. So that's what we call a naked beta. And it's the problem, it's the most problematic background for us because it's a point-like interaction in the detector. The only way that we can identify it as not being dark matter is if we have this recoil particle identification. Okay, I want to say a couple of things about backgrounds. So, I've just walked through for every background, how can we tag it as a background? And if we see something that we can't tag as background, like coherent neutrino scattering, is that really the end of direct detection? In other words, why all this fuss? Why not just model and subtract our backgrounds? After all, it's not like when people discovered the Higgs that they could see every event going by and say, that's a Higgs, that's not, that's a Higgs, that's not. And I'm saying that's what we do need to do in direct detection. We need to tell event by event, was this a dark matter interaction or not? There are a few reasons for that. One is that background subtraction is expensive. If we're looking for a signal on top of background, or the signal small compared to the background, then our sensitivity goes like the square root of exposure instead of with exposure. So that's just stats. And we're always trying to make these these experiments as big and low background as we can, partly to avoid this, but partly also because background subtraction for dark matter is really hard. One of the important points here is that, we typically don't have a smoking gun for the dark matter signal, right? What do our backgrounds look like? Our backgrounds for electron recoils are basically here, or I guess the total electron recoil is here. This is the energy range we're looking at. So it's basically a flat spectrum. For nuclear recoils, it's basically just a falling spectrum. Our signal is a smooth falling spectrum. There's no bump hunting here. So there isn't anything that will jump out, and if you don't have event by event discrimination, there's nothing that will jump out and say, this is signal instead of background based on, say, the energy distribution. So if you wanted to do this without discrimination, you'd have to model your backgrounds and subtract them. But modeling your backgrounds is hard because the only tool you have that's sensitive enough to measure your backgrounds is your dark matter detector. So you have to start doing things like use sidebands. So sidebands in this case means a different energy window. So you might say, knowing what's going on with high energy electron recoils is what we use to tell us what's going on for the low energy recoil spectrum. Because up here, there are features. We could build a background model saying we've got these radioactive impurities at these points in the detector and get that all to match and then see what does that tell us about what we should expect at low energies. But that's hard. It's even harder for the neutrons because there are no features at all in the neutron spectrum. Sorry, I should label some of these. And these are real background projections for LZ. This is nuclear recoils up here. The red curve is coming from neutrons. All these other curves are coming from coherent scattering of neutrinos. Here, this is electron scattering. These are neutrinos. This detector surface plus environment, those are gamma rays. And everything else in here is either a beta decay or a double beta decay. One of our main backgrounds actually comes from the 2 neutrino double beta decay of xenon-136. Okay, so modeling these backgrounds accurately at low energy is hard. And so there are big systematic uncertainties when you do the background subtraction. Finally, we're always in a regime in direct detection where, at least when we're looking for nuclear recoils, we'd like to be able to claim a discovery with, 4 events. And that basically demands that your background levels be down at the, 1 event or less level. So again, background subtractions are tricky, and it's not always obvious when somebody shows you a result, have they done a background subtraction? So there are kind of 2 basic ways people will quote limits. One is this profile likelihood ratio, which is saying we've got, something that we matter. This you can think of as the x-axis here, you can think of as the energy of the thing that recoiled in the detector. And the y-axis you can think of as the particle ID. And in this space, we can discriminate between background. So we've got some calibrated distribution for what backgrounds look like. And we've got some calibrated distribution for what signal looks like. And those distributions overlap, but they're separate. So when you've got these distributions well known, then you can based on the signals you see, do a profile likelihood ratio analysis and say, okay, how much of the red distribution is in there, or in either place a 2-sided interval or a 1-sided interval, a limit on how much of the red distribution there is. Okay, so we go back and ask, is that a background subtraction? Yes, it is a background subtraction, but the PLR kind of naturally focuses your weight on the regions where your distributions don't overlap. It doesn't ignore the regions where they overlap, so it is subtracting your known background distribution, but you're not completely, uncertainties on your background distribution are less impactful if your distributions don't overlap. The other type of analysis people do is kind of a cut and count analysis, where you just say, we're going to make a box, we're going to count the number of events in the box, compare it to what we expected. So here was a result where we were all very happy because we drew a box in position, we saw all these events, and then this was our particle ID down here. In this case, we were trying to distinguish between alpha decays and dark matter. And the particle ID said all of these were background. So we had 0 candidate events in our box. And we said, okay, 0 background event. What did 0 background result? What did that actually mean? Well, what we didn't say was that, what our background expectation was. And in this case, sometimes you do a cut and count analysis and you have a background prediction and you subtract it from your answer. And your background prediction might be 0.1 event, or it might be 100 events. And if it's 100 events, then you really need to worry about the result, because then the systematic uncertainty on your background is very important. If it's 0.1 events, it doesn't really matter. In this case, there was no background model at all. In one sense, that's good. That means there's no systematic uncertainties based on not knowing your backgrounds, because you're not assuming any background model. Basically, what that meant was we were assuming anything we saw was going to be well, we said we had no discriminating capability between background and signal. And what that meant was we knew going into that experiment that it had no discovery potential. It would only ever create a limit. We would say that anything we saw could be signal, but we wouldn't assume that it was, and we just put an upper limit on the signal rate in the detector. So when you just look at the limit curves, you don't see necessarily all this going on. Was this an experiment that could have detected a signal, or were they not considering backgrounds at all? Because you can make a limit without considering backgrounds. If they are considering backgrounds, do they have a big background that they're subtracting, or how sensitive is the result to systematic uncertainties in their backgrounds? And if the experiment's doing a good job, they've taken into account systematic uncertainties in their backgrounds when they make the limit. If they're not doing a good job, they just assumed some background model and told you a result based on that. And I've seen it done both ways on these limits. Okay, so there are a couple things that I didn't get to because we're about out of time. I wanted to talk a little bit about, are there smoking guns for dark matter detection? We might talk about this a little bit tomorrow. There is an annual modulation search that you can do. It's really hard. Dama has seen dark matter for longer than I've been looking for dark matter, and nobody knows what they're seeing. I was going to say a little bit about directional detection as well. I wanted to say a little bit about the neutrino floor, and is the neutrino floor really the end of dark matter detection or not? And starting tomorrow, we're going to talk more about detectors and talk about how does this particle ID actually happen, since if you want to avoid an uncertain background subtraction, this ends up being really important. So that's what we didn't get to today. But we'll pick up with some of that tomorrow. I think if you want to talk about any of these things on the Slack physics channel, then we can keep talking about them. But tomorrow then is going to jump into actual experiments. So, okay, I guess maybe see if there are any other questions that have been coming up in chat.
Yeah, if you have any other questions, please go ahead and stick them in the chat. And I want to say a great big thanks to Eric for this awesome lecture. This is the most fun I've had in months.
Well, thank you.
Okay, unless people are typing still, I don't see anything in particular. Or if you want to raise your hand in the participants list, but I'm not seeing. Oh, here's one question. When you say that the dark matter signal is fundamentally identical to neutrino oscillation, I suspect she means neutrino scattering, and it's the end of direct detection. What do you mean the current background analysis are wrong?
What I mean Yeah, so we can go here just a bit. So the background analyses are not wrong here. So so this is what LZ says their nuclear recoil background is going to be. And most of these backgrounds, everything except the red curve here, those are all coming from neutrinos. They're coming from solar neutrinos. They're coming from atmospheric neutrinos, coherently scattering off of nuclei. We do know what that spectrum is, so we could subtract them. And it's not that the analysis would be wrong. It's just that at that point, instead of building a 10 times bigger detector to get down another factor of 10 in sensitivity, you have to build a 100 times bigger detector. And given that we don't know what dark matter is, we don't know how far down we would have to look. We don't even know if it's this sort of, if this would be the right experiment to look for it at all. It would just be, I think if you're just going to try to fight this with the background subtraction, you'd have to have a really strong case that you were going to see something. You'd have to have hints from something else. That's why people say it's the end of direct detection. Now, if you came up with a really cheap way to build a kiloton dark matter detector, yeah, you would still do it, even if it was digging into the neutrino floor. We just don't know how to do it right now. Are there experiments that do a simple cut and count that wouldn't be able to see a signal like you described? Yeah, so this was a real experiment. And it's not that they can't see a signal. So yeah, I should put labels on these. This was Pico, and this was Lux. These are both from around 2017. And in Pico, it wasn't that we couldn't see a signal. If the signal had been there, we would have seen it. But because we didn't have a background model, we could not have claimed a discovery. We would have just said, we see something, it could be dark matter, it could be a background that we don't understand. And the reason we did that was because we knew there was a background that we didn't understand, that we had tried to get rid of, and we didn't know if we had succeeded yet. So this was an experiment that was simultaneously trying to understand our backgrounds and also along the way saying, well, if the background's gone, we may as well set a limit on dark matter as well. And that's going to be part of the theme for tomorrow, is that so far I've talked about the backgrounds that we can model. There are other backgrounds that are detector pathologies. And usually those are the ones that we actually run into. So no matter how hard we work on our backgrounds, it's just a hard field to be in because of all of the ways your detector can get fooled. Okay, can I briefly describe what the profile likelihood ratio method was again? Okay, so I don't know if Michael described exactly this sort of analysis in his lectures or not. I know he described maximum likelihood techniques. Basically, what you do is you've got a known profile, a known distribution for background. So you have a background model, maybe multiple background models, and you've got a signal model. And you're comparing your maximum likelihood fit. You're comparing the likelihood of your best fit that you get, assuming zero background versus, you're comparing, boy, I don't know if I'm going to be able to write this live. You're comparing the likelihood you get with floating signal to the likelihood that you get with zero signal, and seeing if you get a significantly better fit when you allow there to be a signal. And when you're doing this, you're also having to marginalize over any uncertainties in what your background looks like. And maybe you're actually floating some unknown parameters in your background. Like maybe you don't know exactly how much lead-214 is in your detector. So you make that a free parameter on both the numerator and the denominator here. but you're only allowing the amount of signal to float in the numerator. So you're asking the question, do I get a better fit if there's signal or if there's no signal? And the question that I'm trying to ask here is, how sensitive is that to having a wrong background model? And that's a difficult question. It really depends on how different does your signal look from your backgrounds. If your signal and your backgrounds look very different, you can do this. And this method naturally gives the most weight to events that are very clearly signal and not background, which, you know, you might think were events like this, for example. That's actually a calibration event. The open circles here are dark matter data. The closed dots are calibration data. The point here is that, you know, doing a profile likelihood ratio, it is doing a background subtraction, but it's putting the most weight in areas where the background subtraction doesn't matter. How can cut and count rule out DM? I mean, if we can't differentiate background from DM, it could be that we're detecting DM but wouldn't know. So we would still know if we were detecting dark. No, it's, you know, if we had dark matter, it would have shown up in here. So let's say I'm going to add a dark matter event in here. Blue circles are now going to be dark matter. And in here, that would have shown up as an event in this window. So if we'd had an event, so this happened to be a bubble chamber. So we're literally taking pictures of bubbles. So if we had a bubble show up that, based on our discriminator, which is actually how loud the bubble was, it sounded like dark matter and it was in the middle of the detector, we would have said we had a potential signal event. And we can calibrate our efficiency. So this is also part of tomorrow's lecture. We can calibrate our efficiency for seeing events like that. And we can say with certainty, if dark matter happened, we would have seen it. And being able to say that lets us set a limit. What you need to make a discovery is the converse. You need to say, if we saw something, it was dark matter. So in a sense, if you can say, if there's dark matter, we'll see it, you can make a limit, but you might not be able to make a discovery. If you can say, we don't know if we're going to see dark matter, but if we see something that looks like it, we'll be able to say for sure that it's dark matter, which isn't the case for any experiment. But if you could say that, then you'd be able to make a discovery, but you wouldn't be able to set a limit. The goal for any direct detection experiment is to be able to say both. It's like, we'll see dark matter if it happens, and we'll know it when it happens. In PICO, in this particular round of PICO, we're in this funny area where we could only say, if dark matter happens, we'll know what it looks like. But if we see something that looks like dark matter, it still might be something else. And in that case, you can make the limit. But if you see anything, you're not going to be able to take credit for a discovery.
Okay, I think we're done for this lecture. Big thanks to Eric. Eric, do you have plans to hang around in the coffee break later today, or are you going to be